Welcome to the Extra Space Exploration Series. Following the visit of NASA astronaut Jeff Williams to Singapore, where you get to meet him or hear him at the science centers, at the universities, and in different social settings. We are going to bring you the next 4 episodes where astronaut Jeff Williams is going to bring you on a journey of space exploration. We're going to have 4 episodes covering rockets, the International Space Station, the mission to Moon or the Artemis project, and finally, what everybody is very interested about going to Mars. Well, you can watch the videos, but we have more in store for you. You watch the videos, complete the quizzes, and you get a special recognitions, a certificate on space exploration signed by NASA astronaut Jeff Williams. This is an expired event with the partnership of Science Centre Singapore, Singapore Institute of Technology, and Aeronautics. The second episode is about living in space. Well, we know that humans has been living in space for many years on the International Space Stations. So beside or beyond working on space, doing science experiments, what else the astronaut do? Interestingly, they also push out or launch CubeSat or small little satellites from the International Space Station. Now, one of the companies that developed CubeSat in Singapore is NuSpace, N-U-S-P-A-C-E, founded by Zhening. Now, Zhening attended my course on technology commercialization, and we have actually looked at what are the possibilities and what kind of commercial applications for CubeSat. We look at single CubeSat, we look at constellations. Well, I'm glad to say that Zhening has also launched his CubeSat into space. Let's hear from our Aspire partner, NASA astronaut Jeff Williams.
Yeah, as was mentioned last week, we talked about about rockets in general. I talked a little bit about the space shuttle specifically. And of course, that was the means, the space shuttle, that is, the means to get the International Space Station to orbit, which is an amazing story. And that's what I'd like to focus on today. If we could put up the first slide. This is the International Space Station, of course, that I assume many of you are familiar with. It's an amazing, amazing orbital outpost, orbital facility. And I'll talk a little bit about its assembly. And then in the Q&A, maybe we can get into the details of life, working and living on board the International Space Station. This is pretty much the way it looks as it flies today. This picture was taken from the space shuttle in one of the final missions after the assembly was complete. The next slide is picture that Professor Neal showed. It was a spacewalk that I conducted in 2006. I've done 5 spacewalks in support of the assembly of the space station and also doing some repairs. And the space station was designed so that it could be repairable both inside and outside. And that's why we do so many spacewalks. I'll talk a little bit more about that in a minute. But this picture was taken in 2006 at the end of a almost 7-hour EVA with Thomas Reiter, a German astronaut who had joined Pavel Vinogradov and I for Expedition 13 about halfway through our 6-month stay. And Thomas and I spent the time outside, primarily doing repairs, but also supporting the future assembly of the space station. This was a unique time, and I'll get into it a little bit more, in that it was the end of the period that the space shuttle was grounded after the loss of the Columbia crew and the loss of Columbia, a tragic accident, which I'm sure many of you remember. The next slide, let me talk a little bit about the space station operation itself. If you were to take, consider the equator and go to 51.6 degrees north latitude and south latitude, the inclination of the orbit of the space station is just that, 51.6 degrees. So the inertial orbital plane is at that inclination to the equator, which means we cover this amount of the Earth. We orbit the Earth 16 times a day. That's going 17,500 miles an hour, or about 25,000 kilometers per hour, orbiting the Earth every 90 minutes. So because we're in an inertial plane, the Earth, of course, is rotating under us, and that's why you see the different lines go around the Earth and form a final figure like this, which very well shows the path of the orbit of the space station that we end up covering the Earth. So as we spend weeks and months up there in the space station, we're able to, it's a great observation platform to observe the Earth, and we can watch even seasons go by as we're there months at a time. The orbit originally, before the space station was, International Space Station was envisioned, and that was in partnership with the Russian partners, it was Space Station Freedom, and it was at a much lower orbit. It was more like, as I recall, 23 or 24 degrees, which would have meant that we would have seen very little of the Earth's surface from the space station. We would not have seen most of North America. We would not have seen Europe, and we would not have seen much of Northern Asia. But because of the partnership with the Russians and because of their launch site located at Baikonur, Kazakhstan, it drove the inclination up to 51.6, of which I'm very grateful for, because of its great platform to watch or to study the Earth. The next slide gives you an idea of the order of magnitude of the space station. If you could weigh it today, if you could put it on a scale and weigh it, it weighs almost 1 million pounds. You can see the mass there in the lower bottom center of the screen, 925,000 pounds, nearly 1 million pounds of mass. Of course, it took many, many flights to get that up there, and I'm going to show a video later in the presentation that'll give you an idea of the assembly sequence. The space station is built in components. You could say like a Lego set, or in fact, there are Lego sets out there that where you can build the space station with Legos. But a piece at a time, and the sizes of each piece were constrained by either what a rocket would lift in terms of the Russian segment, or what would fit into the payload bay of the space shuttle in terms of the US orbiting segment. The US orbiting segment also includes the robotic arm, which was a contribution from Canada, as well as laboratory modules from the European Space Agency and the Japanese Space Agency as well. So that's the entire partnership. It's bigger than a football field, as you can see, so it's huge. And most of that area, that if you could take the planform area of the space station, much of that area is taken up by what is depicted here in the picture as blue. They're not actually blue, they're the solar arrays. Those have a very large surface area so that they can capture the sun's energy and produce electricity. And when the sun is shining, that produced electricity is used to charge many batteries on board that are mounted externally on the truss structure that goes across the screen here. And then when we go on the dark side of the Earth, of course, and the sun's not shining, those batteries are discharged to run, to power all of the equipment on board the space station. Of course, there are many computers distributed around the space station that are used to run all the systems, to include, of course, the power distribution system, which goes to things like the thermal protection system, thermal control system, active thermal control, or environmental control, fans and pumps and computers distributed, as I said, all space. So electrical power is very important to us and essential for all of the systems. As I said, it moves at 17,500 miles an hour approximately, which is orbital velocity. So it's a massive orbital outpost. The next slide shows it in pieces. So if you were to blow it up into different pieces, this is how it was sent from Earth, piece at a time, and assembled one piece at a time. If, for example, you look in the lower right-hand corner there, you see those, they're modules, but they look like cylinder-shaped objects. If you added up all of those modules, the silver ones in the lower right and the silver white ones in the upper left, the upper left being the Russian segment, the lower right being the US segment, which also includes the modules from Japan and Europe. All of that added up makes the pressurized habitation portion of the space station. The truss structure that the solar arrays are mounted on that go from the upper right to the lower left, that's all exterior. So if we wanted to do work on the truss structure, we have to go do a spacewalk to get out there. The pressurized volume that we live and work in every day is depicted there with the cylinder-shaped modules. If you added up all that volume, it's about the volume of a 5,000 square foot house. So it's very roomy inside. The standard crew size right now is 7. And that is 3 people on a Russian Soyuz and 4 on a SpaceX Dragon. And we rotate a section of the crew at a time. We typically rotate Soyuz crew twice a year, and we're now rotating the 4 crew members via SpaceX Dragon also twice a year. You're likely aware that Boeing is also produced a vehicle that will be used to rotate 4 crew members at a time. That'll be in conjunction with SpaceX, but that vehicle is still in development. We were attempting to launch a test flight this month, actually earlier in August, but we had some issues that the team is working through, and they're evaluating now whether we can launch later in August or if it will suffer a little bit more of a delay. So currently we have a Russian Soyuz and SpaceX Dragons rotating crew. I've been on board the space station 4 times. The first one was in 2000 when we only had 2 modules on orbit, 1 Russian module and what is referred to here on the diagram as the functional cargo block, which is towards the upper left corner, not too far from the center of the picture. And then node 1, which is lower right from center. Those 2 modules were the only ones on orbit in 2000 when I visited on the 3rd space shuttle flight dedicated to the space station. It was a flight that was conducted prior to Expedition 1 arriving at the space station. So there was nobody on board. We didn't have life support for the station yet up there, so we couldn't have a crew on board. But that was my first visit. It was a 10-day flight on the Space Shuttle Atlantis. And then I went into expedition, which is a term we use to refer to the crews that go to the station and stay there for the long time. And I went into training and spent half my time in Russia because not only training on the Russian segment of the space station, but also training for the flight to arrive and to return to Earth on the Russian Soyuz spacecraft. And I flew that flight in 2006. That's when the picture of the spacewalk was taken that you saw. And that flight was about 6 months long. It was during the time the space shuttle was grounded, as I mentioned before. So we had stopped the assembly of the space station. It was about half done at that time in 2006. During our stay there in the fall of 2006, we started flying the shuttle again and resuming assembly of the space station. My next visit there was in 2009. and went into the spring of 2010. And during that time, we finished the assembly of the space station with the addition of Node 3 and the cupola, which I call the window on the world. It's the only place on the space station where you can see the entire globe of the Earth. The rest of the windows are not large enough to see the entire globe. You can only see a portion of the Earth at a time. So the cupola was a special treat for us, and that was in 2010. And then I returned for my final 6-month flight in 2016 and participated in the full operation of the space station. It's full up and running. Now, you might have heard that although we completed the assembly formally in 2010, we recently added another module on the Russian side just a couple weeks ago. So they have added to their initial design 3 components, and the first of those 3 just arrived on the space station, is currently being integrated, and they will launch yet another one in November, I think, is the current plan. In addition to that, since we completed the assembly, there are some initiatives to add commercial modules on the US segment. So those design details are currently in work. So there will be in the future modifications to the space station. It's, as I said, an amazing platform that still has a lot of potential in the future. We're currently working to technically certify its life extension out to 2030, and we're working with the international partners to do so as well. Currently, we're planning at least to fly it to 2028, and we'll continue to extend it as long as it makes sense within the partnership, and we retain the political support required to fund it. We'll continue to fly it. It's a very critical step toward going to the moon, which I'm going to talk in more detail next week about, and I'll explain a little bit today and then again next week on why this is so critical to get us to the moon. It's the current chapter of space station. The next slide, or space exploration rather, current chapter of space exploration. The next slide, I highlight a few details of the space station. As I said, the first element was launched before my flight in 2000. It was actually launched in 1998 on the space shuttle Discovery. Discovery brought up Node 1. The Russians had launched the functional cargo block just a couple weeks prior. Discovery rendezvoused with it and grabbed it with a robotic arm and attached the 2 together, and that started the assembly. And as I said, we finished it we finished the core in 2010. We actually added another storage module, if you will, in 2011. There were 37 space shuttle flights of the 130 total flights the space shuttle flew in its history. 37 of them were dedicated to the space station, and about 40 Russian launches also were dedicated to the space station to finish its assembly as I defined it in 2010 and 11. So many flights were dedicated to it. Of course, it took longer than we had originally planned, in part because of delays in the technical development of the station components, as well as the significant delay as a result of the Columbia accident and the grounding of the space shuttle for over 2 years. To date, there have been 243 individuals that have been on board the space station from 19 different countries. And that includes not only the partnership, but also includes individuals that flew short flights either on the shuttle or as spaceflight participants, commonly referred to from time to time as tourists on the Russian Soyuz. And I'll leave it up to you to go research the history of those different people that have been on the space station. But that's a significant number of individuals. Personally, I added it up a few years ago, and I think I've been on board the space station with about 56 different individuals from 9 different countries just during my time there, which is an accumulated time of about 1.5 years, 530 some days in space. To date, in the history of the space station, 232 spacewalks have been conducted. And those spacewalks, as I've said earlier, were primarily used to support the assembly of the space station, but also maintaining it, repairing it as things fail, and also deploying some experiments, external experiments on the outside of the space station. I'm often asked what's the reason, what's the purpose of the space station? And I put it here on the slide. And there are 3 primary categories I see in the purpose of the space station. And the first one is, I think, obvious to all of you. It is an orbiting laboratory. I've conducted hundreds of experiments on board during my time there. And as the slide says, there have been nearly 3,000 experiments scheduled on the space station and conducted over its lifetime. And those experiments cover the whole spectrum of the different science disciplines. The primary area of study, I think, that's most significant and most important for future space exploration, of course, is the study of the human body and the impacts of the environment on the human body, so that we can better prepare for leaving Earth orbit to go back to the moon for extended periods of time, and then eventually on to Mars. And of course, you can imagine, many of you know, are very familiar with the impacts of just being in weightlessness and not being able to, for example, sustain your muscle strength. Also, your bones, our bones need exercise, so that's very important. So we have used the space station to develop protocols as well as developing exercise equipment to sustain our strength, both in muscle and bone. Radiation is another area that we're very concerned with. So there's lots of experiments that are conducted to study the impacts of the radiation environment. Of course, when we leave low Earth orbit, where the space station is, the radiation only increases, and it's a particular challenge for going to Mars. It's well understood, or pretty much understood, going to the moon, that we're protected by much of the deep space radiation because of the magnetic field around the Earth. But when we go to Mars, it's a significant problem. You might have read in the news another area that's of medical concern, and that is that about 40% of the crew members that have gone to space station have suffered a change in their visual acuity. Their eyesight has been degraded, caused somehow from the environment. We don't understand it exactly what the root cause is. So there's a lot of research going on to try to find that root cause so that we can develop a countermeasure for that as well. At any rate, a scientific laboratory, which provides a platform that's in a microgravity or weightless environment, is a very big part of the purpose of the space station. Related to that, though, is the technology development. I mentioned the research that goes into exercise. We also have used the station to prove out new technology for exercise, for example. And there's many other technologies that's currently in work, being developed on the space station. We need to, for example, in the life support system, we need to continue to improve the reliability and the performance of the equipment used to remove carbon dioxide in the air. Carbon dioxide is a big challenge. Every time we exhale, of course, we produce carbon dioxide. So we have to continually be removing it from the atmosphere inside the space station. And that has proven to be a challenge. When we have elevated levels of carbon dioxide, it has a significant impact on the health of the crew and the ability of the crew to stay rested and to be able to be at peak performance. So we have new technology currently on board station that promises to improve both the reliability and the performance of that equipment. So it's a great opportunity to develop technology that will be required to go back to the moon and on to Mars. The third area I think that history will show in terms of purpose of the space station is just the operation itself. It is the most complex, extensive space operation ever conducted. In fact, I think it's the greatest technological achievement of humanity in history if you consider both the technical complexity of the space station, but then the scope of its size, its capability, and the fact that it took all those years to put it together, that all of the components come from different countries and different design philosophies, particularly between the Russian side and the rest of the partnership. The technological approaches have been completely different, but yet they were integrated together successfully. The station, the complexity of just assembling the space station was an amazing achievement in my view. In that we had issues, we had challenges, we had problems we had to work through, but nothing significant. When you consider that each major component that was added to the space station was required for all of the subsequent components. If we had any single major failure in the assembly, if we had lost, for example, a rocket that was carrying a critical component, it would have stopped the assembly and likely would have doomed the project. But yet with those 37 space shuttle flights and 40 Russian rocket launches to put it together, we were able to accomplish it. And it continues to go. We've going on 21 years of continuous human presence. We have had a significant number of additional rocket launches supporting it. We've had crews coming and going since 2000. And even in that, we've worked through some issues. We've had some delays in rocket launches, launching crews that we've had to work through. We had one ascent abort on a Russian Soyuz a few years ago that we had to work through. Thankfully, the crew survived that abort and returned to Earth safely, and they were able to later fly their flight successfully and complete their 6-month stay on the space station. But when you consider all of the details of the history, I think that will be a significant legacy of the space station. We can, I'll just show briefly the next slide, and then we can transition to the Q&A. The next slide is, at the time, I didn't know what a selfie was, but this is a selfie. If you have to look at it a little bit close, this is a picture taken during a spacewalk. The black circle right in the center of the picture is the objective lens of a Nikon camera pointing at us. The camera is wrapped in a white thermal blanket. That's why you might not recognize it as a camera. It's being held by my two hands, and I'm pointing in at my face, at my visor, and the visor is plated with gold, the sun shield, to keep the sun's rays down, kind of like a large sunglasses covering the entire globe. And it's a very reflective surface. So now in the reflection in the visor of the spacesuit, you can see not only the arms with the US flag and the EVA patch on the left, but you also see reflected in there the entire space station, the truss assembly going across. You can see some of the modules going from top to bottom. And then behind that, you can see the globe of the Earth. So it's an amazing picture too, to give you a little perspective of the vantage point that we're at here, orbiting the Earth 17,500 miles an hour, hanging on, and in this case, mounted to the robotic arm during a spacewalk, and looking back at the space station below, and then the Earth below it. So it's one of my favorite pictures. Oh, I'm sorry. Yeah, let me show this video here. I like this video because it gives you another idea of the history of the space station assembly. As I said, in 1998, we launched the functional cargo block at Node 1, and that started the assembly of the space station. And then we added a few more components that were necessary to support a crew living and working on board the station, to include the initial power. And there you see the first set of solar arrays. And at this point, that's when Expedition 1 launched. And we've had continuous human presence on board the space station during the subsequent assembly. We added the US laboratory module, we added a robotic arm, we added an airlock in order to do spacewalks, not from the space shuttle anymore, but from the space station itself. And then you can see we started adding that truss structure that goes across the top of the space station. And at this point is when the Space Shuttle Columbia accident occurred. And it's grounded, the space shuttle stopped the assembly, and that's when I spent my time on there in 2006. Then we began flying the shuttle again and resumed the assembly, added another set of solar arrays, continued to build it out, continued to add to the truss structure so that we could add the final set of solar arrays on both the port and the starboard side, added additional modules. Here you see the relocation of Node 2 to the front, which enabled the addition of the European laboratory as well as the Japanese laboratory. And then we added more solar arrays. All of those solar arrays are required to produce the power required to operate the entire space station. So it was all by design, all very deliberate in the sequence. Each of these components were put in place by the robotic arm that Canada had contributed, which is not depicted here, but you can imagine the robotic arm moving around, grabbing each of these components out of the payload bay of the space shuttle and then attaching it to its final. And here we see the mission's final. So I thought that video would be a good video to illustrate the complexity of the assembly, which occurred over those many years.
Now we are ready to do the quiz to participate in space exploration. Sign up to the link below.